Well, we are doing kinematics now, 1D particle kinematics. Um, 1D means motion along a line. Particle means assume nothing has any lengths. It's just like points moving around. And kinematics means position, velocity, and acceleration. And last time we defined position, I talked about sort of the connection between how you go from something happening in the real world that's actually going on and putting that into a set of numbers and defining an object's location as a position. So now I need to introduce velocity and acceleration. So last time I defined the position. And so now I'm going to start with velocity. And velocity is, in everyday speech, velocity and speed are kind of the same thing. You know, like if you watch a baseball game, the announcer will at some point say like, this pitcher has great velocity, you know. It means the same thing as speed. In physics, velocity has one important other bit of information attached to it that speed doesn't. Velocity also has to tell you the direction the object is moving. Okay. So first of all, velocity tells you how quickly the position is changing. And if we call the velocity lowercase v, okay, that's what we're going to do during this class. And we're going to call the speed capital V. It's sort of a common way to denote things like this in math. I know it's a little bit confusing, but the capital V is the speed, what your speedometer on your car says or whatever. Lowercase v is the velocity. Well, then here is the relationship between these two. The velocity is plus or minus the speed. Okay, so in other words, the absolute value of the velocity is the speed. Speed is never negative, it's always positive. And then where do you get the sign from for the velocity? The sign of the velocity is the direction the object is moving. Okay, so for example, let's say we have a car that's moving along a path like this. And let's say we're going to call the positive direction down this hill. And that means the negative direction is up this hill. And let's say that the car is moving this way at 30 meters per second. So this is the speed. You know, that's what its speedometer says. And we want to know what's the velocity. Well, the velocity is plus or minus the speed, 30 meters per second. And now you have to think about the direction. Is the car moving in the positive or negative direction in this case? Negative. And so the velocity is negative 30 meters per second. Okay. Your speedometer doesn't do that. If you think of traveling back and forth along a line as you go from, let's say, you go from here to Duluth and back, okay? And let's call north, you know, the way to Duluth, we'll call that the positive direction. And the way back from Duluth, we'll call that the negative direction, okay? Your speedometer doesn't say 60 miles one way and then negative 60 miles per hour the other way. It just says your speed, which is 60 this way and 60 on your way back. If your speedometer gave velocity instead, then it would say positive when you're going one way, negative when you're going the other way. Okay, that's the relationship between those things. The units for velocity are always units of length divided by units of time. And that means that the SI units are meters per second. So that's what we're going to almost always use for velocity. So how can you read the velocity on, we've talked about position versus time graphs a little bit. How does velocity show up on a position versus time graph? On a position versus time graph, the velocity at a chosen instant is the slope of the tangent line. We're starting to think about tangent lines this week in lab, so half of you have already seen this stuff, half of you will see it today. And so for slope, signs of slopes, remember that something like that is a positive slope. Horizontal is a zero slope, and something like that is a negative slope. Okay, so let's say that we have a position versus time graph that looks like this. Okay, so that's the object's motion. And let's say we want to figure out the signs of the velocities at this instant A, instant B, and instant C. Okay, well, in order to draw the tangent lines, the easiest way to do it is draw two nearby points that are on the curve, on the graph. Then draw the line that goes through those points. What's the slope of that red line? Positive, yep. Now, same thing for B. Draw two nearby points on the graph. Draw the line through it. What's the slope of that line?
0.
0, yep. So at the point B, if the velocity is 0, the speed is 0, so that means that it's at rest at that instant. This positive velocity means at this instant it's moving in the positive direction. And now C, draw the two nearby points on the graph, draw the line through the 2 points. And what's the sign of the slope at C?
Negative.
Yep. So that means this is moving in the negative direction. Okay, let me do another example. Okay, well, so before I go on to the next example, let's think about what this means. So this means that the object, remember, the object isn't following a curved path like this. This is just the position versus time graph. The object is just moving along a line. And we don't know what direction the line is because no one told us that. We just have the stuff from Math World. But we do know that this object is going to start out moving in whatever its positive direction is. Okay. Then it's going to slow down and stop. And it'll be stopped at that instant B. And then it'll start moving in the opposite direction that it was moving in at A. It's coming back the same way, towards where it was before. Okay, so now let's combine both of these two things. So let's say we have a position versus time graph like this. Make that a little curvier. Okay. And the instant that we're going to analyze is just right there. And in the real world, let's say that the object is moving along this path. And let's say we're going to call this direction positive, and this direction then is negative. Okay? And we want to draw an arrow in the real world in the direction the object is moving. Okay? So how are we going to do that? Well, we know the direction that the object is moving is determined by the slope of the tangent line. So I'm going to start on the position versus time graph by drawing the two nearby points on the graph and drawing the line through them. Okay? That's the tangent line. Is the slope of the tangent line positive, 0, or negative? Yeah. The slope of the tangent is positive. So is the object moving in the positive or negative direction? So, yeah, object is moving in the positive direction. And now we can go to the real world. we know that it's moving in the positive direction. Now we need to also know in the real world which way we're calling positive and which one we're calling negative. I said that we're calling positive down the ramp. And so we know that at this instant, the object is moving this direction. Okay? Any questions about that? The next thing we have to talk about is acceleration. And acceleration measures how quickly the velocity is changing. Notice something about that definition. If acceleration is measuring how quickly the velocity is changing, then if the velocity isn't changing at all, there's no acceleration. Okay, so anytime you have constant velocity, that means the same thing as zero acceleration. Constant velocity is zero acceleration. Now, there is a difference between what acceleration means in 1D and what it means in 2D and 3D, okay? Right now, we're dealing with 1D, just motion along a line. In 1D, acceleration, non-zero acceleration means the speed is changing. In 1D, any acceleration changes the speed of the object. And I want you to start getting used to this idea now. We're not at 2D stuff yet, but in 2D, it gets a little more complicated. It can mean speed change. Or it can also mean that the object is turning. So, like if you know the feeling of doing sort of a tight turn in your car, that feeling the seatbelt is holding you in place. You kind of have this feeling in your stomach. That is the feeling of acceleration. And you can take that turn at a constant speed and you'll still have acceleration happening because you're turning. Okay? There's no such thing as turning in 1D. All you're doing is going this way and then back, So there's no way to change the direction you're going. All you can do is slow down, stop, and then start going the other way. Okay? For interpreting the sign of the acceleration, it has to do with whether the object is speeding up or slowing down, but probably not the way if you had to guess what the sign of the acceleration meant. I mean, first, sort of an unfair question to ask you that, like I'm just starting to talk about acceleration. But if you had to guess what positive or negative acceleration meant, you might think, oh, well, I'll bet a positive acceleration is speeding up and a negative acceleration is slowing down. It's a little more complicated than that, so you have to be careful with this. If the velocity and acceleration have the same sign, the object is speeding up. On the other hand, if velocity and acceleration have opposite signs, the object is slowing down. The units for acceleration are units of length divided by time squared. And so the SI units for acceleration are meters per second squared. Okay, so now, just like with velocity, I said, so now we thought about how to interpret a position versus time graph to understand the direction of the velocity, the sign of the direction. So let's do the same thing with acceleration. So on a position versus time graph, how does acceleration show up? The acceleration is shown by the curvature of the graph. So it's shown by the curvature of the graph at the desired instant. So if at the desired instant you have part of a concave up curve like that, the acceleration is positive. If you have no curvature, then you just have a line of some kind. It could be like this or like this or like this. But if there's no curvature, then the acceleration is equal to 0. So what's happening to the velocity at a place where the position versus time graph is a line? It's constant. Yep, it's staying the same. And you could figure out what direction the velocity is based on the slope of that line. And then the last one is if you have part of a concave down curve like this, that's a negative acceleration. And this is actually easy to remember because this is like a positive mental outlook and this is a negative mental outlook. Okay, so for example, let's say our position versus time graph looks like this, okay? And the point well, let's choose a couple points. So let's say there's one and there's one. And we want to know what are the signs of the acceleration at the points A and B. Well, if you're at this point A, you can see that at that point, it's on a concave down curve. Do you see that? And so concave down means the acceleration is negative. So at A, the acceleration is negative. But it doesn't stay concave down. Somewhere in here, it switches from being concave down to concave up, okay? And so by the time you're at B, you're on part of a concave up curve. And so at B, the acceleration of this object is positive. Where would the acceleration be 0? Somewhere in here, there's a point where it switches over, and at that switch over point, the concavity just at that instant is 0. So let's say maybe right here or something, you know, and at that point, just at that instant, the speed isn't changing. Let's also think, okay, so let's say this is the first part. And now the second part, let's say at A and B, is the object speeding up or slowing down? Well, to answer that question, you need to know not just the sign of the acceleration, we know those, you also need to know the sign of the velocity, because a thing is speeding up if acceleration and velocity have the same sign, and it's slowing down if they have opposite signs. So let me draw the two nearby points here. That is the tangent line at A, and let me do the same thing at B. That's the tangent line at B. So in both of these two cases, the velocity is positive because that has a positive slope. So at the point A, we have that the velocity is positive and the acceleration is negative. So is the object speeding up or slowing down at the point A? Yep. So these are opposite signs. So it's slowing down. And at B, the velocity was positive. The acceleration is positive. They have the same signs. So the object is speeding up. Okay, so what's going on here? This object starts out moving in the positive direction. It slows down until it stops. Then it starts speeding up, now in the negative direction because the slopes are negative. Then it slows down again until it stops, and then it starts speeding up again in the positive direction. So by interpreting, knowing how to interpret the velocity and acceleration from a position versus time graph, you can see that this thing is, you can see what it's doing, going one direction, slowing down, stopping, speeding up the other direction, slowing down, stopping, and then speeding up in the original direction. Okay, so let's do another example sort of similar to the one we did with velocity. And let's say the position versus time graph looks like this, and this is the point that we care about. And over here in the real world, the object is moving along a vertical line, and we're calling the positive direction down, and that means the negative direction is up. And we want to determine the sign of the velocity the sign of the acceleration, we want to draw the directions, draw arrows in the directions of velocity and acceleration in the real world. And then last, is the object speeding up or slowing down? Okay, well, to get the sign of the velocity, draw the two nearby points, draw the line through it. So the tangent line looks something like that. Does that tangent line have a positive, zero, or negative slope? Negative. Yep, so the velocity is negative. Now the concavity, is that part of a concave up, like a smile, or a concave down, like a frown? Yeah, so the acceleration is negative. And so now let's go to the real world and draw these things. Both of these, the velocity and the acceleration, are both negative. Negative is up. And so you can say the velocity is this way, and the acceleration is also this way. And then the last thing, is this object speeding up or slowing down? Well, the sign of velocity and acceleration are the same. So this object is speeding up. Okay? All right, well, for calculations, for now, the only kind of accelerations we're going to see are constant accelerations. So accelerations that don't change. We won't be doing calculations for things like this, because this has a negative acceleration for a while and then a positive acceleration for a while, so it's not constant. Okay. But the calculations we're going to use, are going to use the constant acceleration equations. And the rationale for using the constant acceleration equations is, it's definitely true that not every motion has a constant acceleration. So not every motion has constant acceleration, but it turns out that some important types of motion do. Okay, and that's why this is useful. So not every motion has a constant acceleration, but some important types do. And probably the best example of this is objects in free fall or projectile motion. So let me first introduce these three constant acceleration equations. Then I'll talk about the general steps for using them. And then we'll just spend a little time, maybe today or maybe not till Monday. We'll see how far we get. But just doing some problems and seeing how these fit together. Okay, so to define the constant acceleration equations, we're going to say P sub I and V sub I. Let P sub I and V sub I be the position and velocity when time is equal to 0. And then we're going to define these other position velocity, P sub F and V sub F. And we're going to let those mean the position and velocity at time T sub F. Okay, so that F is for final, the I is for initial. That's what those letters come from. You can think of time equals 0 as when you click the stopwatch on to time some motion. And time final is when you click the stopwatch off to look at the time. To read the elapsed time. Then with those definitions, here are the constant acceleration equations. The first one says V sub F is equal to V sub I plus A times time final. The second one says P sub F is equal to P sub I plus V sub I times time final plus 1/2 A times time final squared. And then the last one says 2 times A times the quantity P final minus P initial is equal to V final squared minus V initial squared. So those are the three constant acceleration equations. A couple things to notice. Only one of these equations doesn't use the elapsed time. Okay, so if there's no times in your problem at all, then you're probably going to end up using this one with no times in it. And the other thing is the positions and velocities, notice we're always talking about either at the instant you turn the stopwatch on or the instant you turn the stopwatch off. Acceleration doesn't have that. Acceleration is just what it is, and that's because we're assuming that the acceleration is constant. Okay, so the starting acceleration is the same as the final acceleration, and it's the same as the acceleration the whole time in between. Okay, so here's a set of steps that work for using these constant acceleration equations. So the first step is you have to choose 4 things. And this is related to when we were talking before about before you can draw a position versus time graph, you have to choose an instant that corresponds to turning on the stopwatch. When are you going to turn the stopwatch on? You have to choose a reference point, so something that you're going to call 0 position, and you have to choose which direction is positive and which is negative. So the first thing you have to do is choose, and these choices are in the real world. You know, this is like you can imagine putting tape on the street or, you know, putting an arrow in this direction on the street. This stuff is all happening in reality. So choose a location that you're going to call position equals 0. And you're going to choose a positive direction. And a key thing to remember here is that these are totally up to you. You can make any choice you want of these 2 things and do the problem right. Sometimes certain choices make a problem easier or harder, but any choice will work. So these are up to you. The other 2 choices you have to make are an instant when you're going to turn on the stopwatch. So that's the time equals 0 instant. And the instant that you're going to turn off the stopwatch. So that's the time final instant. And these are almost always either you did it right or you did it wrong. If you make the wrong choices of these, then you can't do the problem. So how do you know what instants to choose? You want to choose these at instants where you're given information. Or where you're trying to find information. Okay. The second step is to go through all the variables that appear in the constant acceleration equations. And there's just 6 of those variables, so you can always go through them in the same order so you don't forget them. So here are the 6 variables. Time final, acceleration, P initial, P final, V initial, and V final. 1, 2, 3, 4, 5, 6. Bless you. So out of those 6 variables, list which ones you know and which one you're trying to find. The third step that most of the time is the last step to this is you want to look for an equation out of those three that I gave you here. Look for an equation that has the variable you're trying to find. And every other variable in the equation is known. Once you find that equation, just plug in the values and solve for the one you want. This just comes from the fact that one equation can only solve for one variable. So if you have more than one thing, if you don't have the thing you're trying to solve in it, obviously that equation can't give you what you're trying to solve for. And also, if you have more than one unknown in an equation, you can't solve for anything. So you just want the one unknown in that equation to be the variable you're trying to calculate. Sometimes you can't find an equation that works, and so I'm going to put this fourth step in parentheses. If you're lucky, you don't have to do this, but if no equation works, then instead try to solve for either time final or acceleration. And then go back to step 2 and try again. Okay, so that's it. And I think it would be a good idea at the start, at least, to print this out or have the sheet out beside you as you do this, to just keep making sure that you're following all the steps of doing this. Eventually, you'll do a few of these problems and then it'll start to become ingrained. But for now, you want to make sure that you're not missing any of this stuff. Okay, so now I'm going to just go through some examples of how to use these. So let's say a car is traveling 40 meters per second and hits the brakes. The car stops 30 meters away from, so it takes 30 meters of travel for the car to stop. And we want to know first, what's the car's acceleration? And second, how long does it take in time to stop? All right, well, I'm going to just draw a little picture of what's going on. So here's the car. It's going this way, slowing down. Let's say this is where it hits the brakes. This is where it stops. So when it stops, it's at rest. Its speed is 0. And we know that the distance between these 2 points is 30 meters. And so we need to start by choosing in the real world where this picture is drawn, a 0 position, a positive direction, a time equals 0 instant, and a time final instant. So what do you want to choose as the 0 position? Remember, this is the one that you could choose anything and this problem would work fine. Most people would probably say, might as well choose the 0 position to be where the car is when it, when the motion we're analyzing starts. So let's call this the 0 position. And then most people would also say, might as well call the positive direction the direction it's moving. Okay. And now what about the 2 instants? Basically, where are we going to want to turn on the stopwatch and where are we going to want to turn off the stopwatch? So time equals 0. What instant is that going to be? Remember that this is always going to be based on an instant when you're trying to find information or an instant where you're given information. We're given stuff about the speed when the car hits the brakes. So our time equals 0 instant is going to be when the person hits the brakes. Okay, the start of the deceleration. And then for part B, we're going to try to figure out what time final is. So our time final is going to be when it comes to rest. For part A, we're not really trying to find anything at a specific instant, but we're given information when the car comes to rest. We know that its speed is equal to 0. Okay, so our time final instant is going to be when the car reaches rest. And now we're going to list out the variables that we know and the variables that we're trying to find. Okay, so this first one is just for part A. I'm going to list out the variables and we're just going to go through them one by one. Okay, do we know the amount of time that it takes for the car to stop? Like, do we know what the stopwatch says? No. But for now, that's not the thing that we're asked to calculate, so I'm just going to leave it off of everything. Do we know what the acceleration is? No, but that's the thing that we're asked for. So we're trying to calculate A. Okay. Do we know, remember the meaning of P sub I is this is the position of the car when time is equal to 0, when the stopwatch goes on. Based on our 0 position and our positive direction, do we know the position of the car when we turn the stopwatch on? Yeah, we do. What is it? 0, that's right. Because that's just where we chose the 0 to be. So for PI, that's equal to 0. Do we know the position when we turn the stopwatch off? Do we know the position of the car when it comes to rest? Yeah, we know that if you start at 0 and go 30 meters in the positive direction, the position is going to be positive 30 meters. So P sub F is, I'm going to just be explicit with the signs of these for now. So I'm going to call that positive 30 meters. And now what about the velocities? Do we know the velocity of the car when time is equal to 0? We know the speed is 40 meters per second, okay? And we know the direction, so we can put together the velocity. So the velocity when time is equal to 0 is, you can think of it as plus or minus 40 meters per second. And now is the car moving in the positive or negative direction? Positive, so we want the positive there. And then do we know the velocity at time final? It's come to rest. Yep, so V final is 0. Okay, so are there any of those constant acceleration equations that have A in them and everything else that's in them is listed here? And the equation that works is this one, 2A times the quantity PF minus PI is equal to VF squared minus VI squared. I don't make you do this anymore. I used to. So if you look at the solutions, I'm gonna, all the solutions will have this, but you don't really have to worry about it. If you put the units into any physics equation and do the math correctly, the answer will come out with the units that it should for the, so like, if I put in the units along with all of these values and calculated A, the units that would come out for A would be meters per second squared. Okay, so you don't have to worry about doing that, but I just want you to know that it does work. And sometimes it can be a useful way to sort of sanity check your work, make sure that you didn't make any dumb mistakes. If the units come out wrong, then something went wrong, you know. So I guess maybe I'll do it once and then I won't do it anymore after that. So we have 2A times the quantity. P final is 30 meters. P initial is 0. And that's equal to V final squared minus V initial squared. So that's 40 meters per second squared. So if you multiply all this together, you get 60 meters times the acceleration is equal to, if you square 40, you get 1,600. Square meters, you get meters squared. Square seconds, you get seconds squared. So this comes out to be 1,600 meters squared per second squared. Now divide both sides by meters, and that cancels one of those two. And now divide both sides by 60, and you get that A is equal to, yeah, 26.6 repeating, and the units are meters per second squared. And what did I do wrong? I did one thing wrong. This 40 squared, notice that negative is not in the parentheses. So you're not squaring out that negative. So I just drop my negative here. And that means that this should be negative. If I hadn't noticed that I made that math mistake, how could I pick that up? Well, if you think physically about what's happening, you can usually catch stuff like that. We know that this car is moving in the positive direction. We know that it's slowing down. And so that means that the acceleration has to be the opposite sign of the velocity. So we expect that acceleration to be negative. Okay? Anybody have any questions about that? All right, so there's the acceleration, and now we want to find the elapsed time. So first of all, is there any reason that we need to change the instant for time equals 0 or time final? No, those will work fine. Sometimes we'll see problems where you're going to have to change those. like that would happen if it asks you something about a different instant, you know? But these will work fine. So all of those 4 choices are going to stay the same. And so now we can think about what we know and what we want. If your choices are the same, then any variables that you know stay the same. So anything that we knew above here, we can put in the known column. And we just calculated the acceleration. So we know that the acceleration is negative 26.6 repeating meters per second squared. Initial position is 0. Final position is 30 meters. Initial velocity is 40 meters per second. Final velocity is 0, and the thing we're trying to calculate is time final. Okay, is there an equation that works to solve for time final? Well, if you look at it, let's look at both of these two. So V final is equal to V initial plus A TF. And then also let's look at P final is equal to P initial plus V initial TF plus 1/2 A TF squared. Okay, so what we want is for TF to be in the equation, and everything else in the equation should be listed in the known column. So let's look at this first one. VF, known, VI, known, A, known, and TF is in it. So that'll work, okay? And let's look at this second one. Again, TF is in it, so that's good. And then what about the other things? PF, yes. PI, yes. VI, yes. A, yes. So either one of those would work. So what happens in that case? Might as well use this one because it's the simplest one. There's no squares to worry about. Squares can be a little bit of a pain because it obscures the sign. You know, if you square a negative, you get a positive. So anyways, anytime you get that V equation to work, use that. And so I'll plug in these values. This time, I'm not going to keep the units. So VF is 0. VI is 40. Acceleration is negative 26.6 repeating times time final. I'll subtract 40 from both sides. So you get negative 40 is equal to negative 26.6 repeating times time final. Now divide both sides by negative 26.6 repeating. And you get somewhere around 1.5 seconds. So TF is equal to 1.5 seconds. Anybody have any questions about that? Okay. Well, I'm going to give you a couple of problems like this to try to do for Monday. As you do them, if you're confused about it, write it down, and I'd be happy to go through those problems on Monday. But then we're going to spend, after we get through with that stuff, we're going to spend most of the time Monday. I'm just going to write problems up here. I'm going to give you time to try to think through the steps, and then I'm going to go through it, and you can compare what you did, what I did at every step. Okay? So that's it. Be careful out there. Is it still like super slippery?